So hello, everyone. It's my pleasure to introduce today's speaker, Stephan Saalfeld. Stephan is a group leader at the Janelia Research Campus here in Ashburn in the US. He's one of the founding authors of CatMate, ImageLab2, Big Data Viewer, and Tera, as well as the creator of the N5 API and the N5 format. His lab develops image analysis methods for large data sets, mainly for 3D electron microscopy and 3D light microscopy, and they actively contribute to various open source projects. Before joining Janelia, he worked as a postdoctoral fellow with Pavel Tomacek at the Max Planck Institute for Molecular Cell Biology and Genetics in Dresden, Germany. Stephan holds a PhD in computer science, as well as a diploma in computer science and media from the Technical University in Dresden. From 2002 until 2008, he was a co-founder and member of the freelance developer network Phänomen.de, where he developed commercial web applications. Today, he's going to talk about scalable open source methods and tools for large microscopy volumes. So we are very much looking forward to your presentation, Stephan. Please feel free to share your screen and take it away.
Thank you, Ulrike. So first of all, this is exciting. I've been following this interest group over the last year because I had nothing else to do. No, sorry, but it's a nice distraction. It was always super interesting. Today, so what I'm going to talk about is mostly not super brand new stuff, but things that I thought would tailor a little bit to the interest of optically focused folks, and that we haven't published so well, or like buried in the supplementary material of some other papers, and so they may have gotten lost. People from Janelia will probably recognize a lot of things. So the first part of the talk, at least, will be a little bit boring for them. While creating the presentation, I also figured that I ran short of time, so I will not get much into the last part that I promised. So I will not talk much about organelle reconstructions on electron microscopy, which is the most recent work with the COSIM project at Janelia. But you will have a chance to hear about this very soon from various corners, because this is something that is just coming up. But I will show you some data. Okay, so just as a little bit of a background, in my lab we work on large-scale image analysis problems. We try to make software that is scalable and can be deployed on remote compute environments and on clusters and deal with large data sets. In the past, we have contributed to a number of projects at Janelia that generated such large data sets. For example, here you see the so far only complete Drosophila brain imaged with electron microscopy, together with Khaled and Eric from Scientific Computing. We stitched and aligned this series. Consists of about 7,040 nanometer sections, each consisting of up to 2,000 overlapping tiles, imaged at 4 nanometer lateral resolution with custom transmission electron microscopes. Here is another example. This is the recently become popular HemiBrain dataset, together with then Janelia fellow Dagmar Keinmüller and the same colleagues from Scientific Computing. We developed the methods to stitch and align a volume of this of the Drosophila central brain. This dataset was imaged with focused ion beam scanning EM at 8 nanometer isotropic resolution after it was sectioned into 13 slabs of 20 microns thickness. Here we had to stitch and align the FIB-SEM slabs and then unwarp and align the slab series. And as a last show of example, we developed the code to stitch tens of thousands of 3D tiles imaged with lattice light sheet microscopy, including a method to estimate and correct the flat field of the imaging system from all the tiles by statistically evaluating the intensity distribution across all pixels. But I will start with something more practical, which we faced in every optical system so far when we tried to stitch and overlay tiles and to correlate color channels, and that is the distortion of lenses. Many years back, Verena Keinig at the ETH in Zurich, together with Albert Cardona and colleagues, developed a method to identify and compensate for lens distortion in electron microscopes. And the interesting aspect of this work was that she could do this without calibration grids or anything, by just using a grid of overlapping tiles that would image the same piece of tissue in a highly redundant way. This method works in that it identifies key points in these images, correlates them, and then tries to identify two things at the same time: a montaging function, some affine transform in the original publication for each tile, and a warp function, which is an arbitrary degree polynomial for that is the same for each tile, which minimizes the displacement between all these key points. And we got in contact because Verena would use our implementation of a popular landmark point and feature descriptor implementation, SIF features. And so we together embedded this method in Fiji and made it available in TrackEM2 and expanded upon this. And this is what I want to describe now. So when you do this, you can actually run this and alternatingly optimize for alpha, the lens distortion, and the montaging function, and you can rectify all these images, and then you can apply this transformation to all future incoming images if the lens is constant, right? So one of the issues with this method is that in the original formulation, Verena would use an affine transformation for this A part here, which means that the images can be arbitrarily sheared and stretched and scaled. That's undesired, but what you can of course do is you can replace this with a rigid transformation or something even further constrained, depending on how much you know about the stage of your microscope that you used to generate this grid. Another interesting thing is that if you even if you use a rigid transform and your images are still scaled or sheared or something like this, and that shearing is consistent, then you will still preserve that. And our intent is obviously to make things super isotropic. So a solution to generate an isotropic camera model would be to image the same sample twice, rotated by 90 degrees and unrotated, and then solving a combined problem with a rigid transformation here, because that wouldn't allow this shearing, and it would undo the shearing in all images because you generate an average montaging model, right? Okay, so you should do this when you can, but you can use the same approach to calibrate images from multiple camera systems. And in the EM example, we actually did this because Davi Bock's camera system consisted of 4 cameras per each microscope, and he also had two microscopes of this kind, and then another one that was experimental, and all these cameras had slightly different distortions. And we want an average camera of all of these things. So how can you do this? You can actually do the same thing that I suggested here, namely imaging rotated stuff. You rectify a grid from camera 1. You do the same thing for camera 2. So now we see they have slightly different scaling factors and shearings because the cameras are different. But if we image the same tissue in both cameras, a joint montage with a regularized transform for all these tiles, which should be an affine that is regularized with a translation model or a rigid model or something like this, to find the average shearing for this. The more average your eventual model will be. So how is that relevant for optical microscopy? It's exactly the same problem. It's a little bit easier because the models in optical lenses are usually a little bit better constrained than in the electron microscope, where the lens distortion is generated by charging artifacts, so it's not necessarily spherical or doesn't follow any barrel or percussion distortion model or something like this, right? So the arbitrariness of this polynomial model is more important in electron microscopy than it is in optical microscopy, but it also doesn't hurt in optical microscopy. So together with Janelia's Fly Light project, these fabulous people here, we looked at calibrating the lenses of their confocal systems because we had to learn that when we want to image fly brains, so they image them in several tiles because the images are very high resolution, and you would stitch them, you would get these weird fuzzy areas in the stitching overlap areas, and was impossible to compensate this by just moving images around or by simple models. And turns out that the lens was obviously distorted. And so we tried to establish a good setup for calibration tiles, so good texture. So since they are imaging brains, the first idea was, why don't we throw all the brains that weren't properly prepared onto a big heap? So we generate a brain pile or brain heap, and we image that brain heap, and we established a lens correction model for that. And that indeed worked. But unfortunately, the staining in this sample fades out very quickly. So you can't use it very often, and so you need a lot of brain heaps when you have to recalibrate your microscopes, and that's a little bit unfortunate, right? So we tried this with several samples, and you can use them like once or twice, and then you don't see anything anymore. So that's not great. So we're looking for more reproducible samples. And Jeffrey tried a bunch of things that he collected from the street. This is a paper sample. Unfortunately, the paper sample doesn't have good 2D features, so all these things are lines, so you can't find a lot of spot coordinates. That's not so great. Dirtier paper has a few more 2D coordinates to find, but it's still not very great. And what turned out to be fantastic is a simple bead sample with just a densely populated set of beads. And Jennifer Colonel created a protocol where she stained these beads so they're visible across the entire spectrum. We'll see later that we can use this to calibrate it across color channels, right? So it turns out that these bead samples, so we started with 48 nanometer fluorescent beads, but eventually we used them across the entire color spectrum. It turns out that even if you don't manage to image them very nicely and you have focusing issues and stuff, it still works because you can still find coordinates in these places, and their localization is reasonable enough for this thing. One of the problems that we had with these bead samples is that they would always sync on the cover slip. So we had basically one plane in the imaging system that we could calibrate for. And at least to me, because I'm not an optical person, it wasn't clear whether the lens correction model that you estimate this way would be consistent across all Z levels, because you're changing something to refocus the microscope, right? And so we tested this with the brain samples, and this is what I'm going to show you now in this slightly complicated looking graph, but I'll explain it step by step. So the font I know is very small, but it should be readable on your screen. So I tested this in the resolution that I have here, and if you can't read it, you can make the image a little bit larger, and then you will be able to read it. Okay. So what we see in the right corner of the diagram. So first of all, we have rows and columns, and they're the same. Here is they're labeled with the microscope and the sample that we're using, and some other properties, and we compare things, obviously, right? So this is a square matrix to compare stuff. Since the comparison that we're doing is symmetric, we can use the right corner and the left corner for different things. And what we see in the right corner is a color intensity plot of the camera model compared to another camera, right? So here we compare the identity to the identity, and the difference is 0. So along the diagonal, the difference is always 0. And here we compare camera models with other things. So in the first row, we compare every camera model with the identity. So that's the actual distortion model. And here we compare the difference between camera models. Okay. So to explain the colors, red's pointing up, green is pointing this way, and blue is pointing that way. And for everybody who has color deficiency, I'm very sorry, but I needed 3 colors here. But what you see what you will appreciate is that there are a lot of colors, and that's mostly what you need to understand in this plot, right? Okay. So then here, the lower part is kind of a histogram. So I sampled all locations in these camera images, and we look how much they deviate from each other. So is the top left pixel, how far away is the top left pixel in this camera from the top left pixel in that camera? So in the center, we have 0. And then we have these circles, and each of these circles is 1 pixel. So the green circle here is 1 pixel, the yellowish circle here is 2 pixel, the orange one is 3 pixel, and so on, right? So if things are within this 1 pixel range, like here in this example, then the difference is subpixel. That's great. If it exceeds it slightly, like in this example, then it goes beyond 1 pixel, and the question is then, where does it do this? And for this, you can refer to that plot here, where you see that okay, there's a little bit of stuff going on in the periphery, but then the center is mostly black, so that's fine. Okay, so what we're comparing here now is the same microscope. So we all have scope 3, and we have different samples. We have the bead samples and the chemically tagged brain samples. And we look at the brain samples at 2 different Z levels. And for the beads, of course, we don't, right? So we have 2 bead samples that we compare, and we look at 2 Z levels in the chemicals. Like so what we see, first of all, and that's interesting. So we can use the bead samples because the Z doesn't have any effect, because the Z step 50 and Z step 250 is basically subpixel the same. That's great. Now, when we compare the chemical fixation with the bead samples, we see that the difference grows a little bit. So the majority of everything is still in the subpixel range, but there is a little bit of stuff that goes outside. So, and this is what I pointed out earlier. It's interesting to know where that problem sits, and it mostly sits in the periphery. And the explanation for this is that in the brain heaps, the texture is not evenly distributed. So things are a lot sparser than in the bead samples, which means that the model is actually worse than that in the bead sample, because we don't necessarily have the periphery labeled so well. Okay, so that's great. So from now on, we can focus on bead samples. And in the next slide, we want to show how this compares to other bead samples on a different microscope. So we have a different microscope. We do exactly the same comparison. Again, we see Z doesn't matter. There is a little bit of a difference between the brain heap and the bead samples, but it's still minor. And the bead samples apparently seem to cover the spaces. So this is consistent. That's great.
Sorry, just a very brief question. So one would actually expect, when you have different samples and when you right now talk about lens distortion, that the distortions would be everywhere the same when you only think about what the lens contributes. But right now, you're actually not necessarily looking at the lens distortion, but you're looking at the distortion which the sample adds to the lens distortion, right? No. We look just at we look at the estimated model. We don't know what the correct lens distortion is. This is an estimated lens distortion.
Okay. Yeah. Right. So since I don't have ground truth, one could probably get a ground truth from a calibration grid. But I'm not actually sure if this would be much better than this one, because you would have to be very precise in localizing these cross points to get to the precision that you reach with this. Right, so we're comparing estimates of a lens model from various samples on different microscopes.
Okay, then I get it. Thank you for the clarification.
Sure.
Thanks.
Sorry, that was probably not clear enough. Okay, so here we see that on a different microscope we have a very similar outcome, and now we can compare between different microscopes because obviously it's interesting. They're all the same manufacturer. They're all the same size system. Can I estimate the lens deformation on one microscope once forever and then use it for eternity, right? And that would be wonderful because I would have to do it again. And it turns out this is not the case. So what we see here is microscope 1 with the bead sample 1, and here microscope 2 with bead samples. Let me see. So I'm using the 2 different bead samples. We see here that the difference between the 2 bead samples is again within this 1 pixel range, which is great. So the sample itself doesn't make a difference. And the same holds true for microscope 2. But when I'm comparing across microscopes, the difference gets a little bit wider. And this is also wider spread. So it's not just the periphery of images, but we can see that there are differences here in the center. And weirdly, they're also kind of orthogonal and planar. And the only explanation that I have for this that would make sense in my eyes is that the optical system, these microscopes, does not only consist of lenses, but there are also mirrors involved, and they may just introduce these XY artifacts. But probably somebody of you has a better idea.
Hey, Stephan.
Yeah, go for it.
It seems a bit weird. This could this be sort of artifact from the tiling? So if you change the width, the overlap.
Mm-hmm.
So one thing I would test is to change the overlap and see if those stripe position change. So do like 80% overlap or 40% overlap and see if these things change with that. Because it might be like a strong edge artifact that introduces these things.
Yeah. So what I'm confused about is that we don't see this here, right? And we only
you kind of see that. No, you can still see some stripiness.
But it's almost.
It's way weaker because you have this strong edge artifact, but maybe this edge artifact is actually what's causing everything. And yeah, I don't know.
It's an interesting point. We haven't tried this. We usually use like 60% overlap, but it's also not super accurate. Which is so these calibration sets with overlapping tiles are actually better when they're totally random. But if this is
that's what So when they're totally random, if you still see this, then my hypothesis is wrong.
Right. Yeah.
And they do use mirrors to scan. So I don't know. That's what you Right. Cool. Thanks.
All right. Yeah, it's a good idea. Okay, so similar comparison when we look at microscope 1, 2, 3, and 4. So we have all different microscopes, and we see, okay, this is reproducible. So the difference is notable. It's more than when we're just in the same system. And we also figured that over time these things change. So after each time a technician comes in and calibrates the system, we'll have to do a new lens correction model, which isn't terrible. But because it's like, I don't know, once every 6 months or something it is. But since currently it's a little bit manual, and I will show you how you can reproduce this, it usually falls on me to do this, which is fine. Okay, so here's another example. Same result. Sometimes you see more of these artifacts. Sometimes you see fewer. But it turns out that all these microscopes have a little bit of a different model. Okay, so when we now practically apply this, what's the effect? Here we see a stitch brain from Alyosha's multicolor flip-out datasets, and I don't know if I can flip and forward. So yes, exactly. So one of the issues with the older datasets was that the metadata did not contain information on which of the 6 microscopes in Flylight the image was acquired, which is a bit unfortunate if you're trying to estimate a lens model in hindsight. But it turns out that you can do a little bit of archaeology. because one of the measures that you get out during stitching is how well tiles correlate when you stitch them. And you can use and you would expect that if your lens model is better, then the correlation between these tiles gets better. And this is exactly what happens. So we can stitch these data sets with all lens correction models. So we see when we don't apply lens correction, the correlation is, of course, worst. Not exactly, because the scope 6 model is also kind of weird, or at least something is different in this microscope than with the others. Then for all scope 1 to 5, things look better, improved. So they have similar lens models. So I mean, you've seen the color diagrams. They're not completely different from each other. But we also have a very clear winner. So this data set was obviously acquired on microscope number 5. And so with this little bit of hindsight archaeology, you can figure out which of the systems you had. If you have a zoo of lens correction models, you can test them all if you have no idea at all, and you can try which one makes your stitching best. Okay, so practically, I don't know, when we switch before and after, this is probably not something you can see over a Zoom presentation, and you also don't see which one is better when we zoom out so much, but it's much more clear when we zoom in. So here on this side, we see the stitching we saw before lens correction, and on the right side, we see it after, and we can I can switch between the two things. We can appreciate the difference. And since we're using an averaging blending, it is very clear that post-lens correction things get a little bit nicer. And the same thing is true here. And I actually like this example in particular. So if your contrast is correct, you can actually see that this white stuff here, which is the reference channel for synapses, seems to sit stable behind these moving green channels. So we have a little bit of a parallax effect. And this is because we calibrated, so we considered every color channel an independent camera. And we did this multi-camera adjustment that I talked about earlier that we initially developed for the TM microscopes, which now serves the purpose of aligning the different color channels and removing chromatic aberration. So we get an independent lens correction model for all color channels that overlaps these color channels better, and so the co-localization between color channels becomes vastly improved. Okay. So much about this. Code and tools are available in TrackEM2, which is part of the Fiji distribution. And then there is a little repository with helper scripts on our GitHub repository. And then there is this very long and extremely boring YouTube tutorial where you can watch me slowly grinding through all this stuff and calibrating a camera for fly light. So for one scope with 5 color channels. And it's very easy to reproduce. And yeah, so if you have interest in that and want to try it, then please do it. And if there are questions, you can always get back to me. So this was extremely useful and instrumental to create a better atlas for the Drosophila brain, because now we could stitch brains without overlap artifacts. And this is what John did together with Flylight. These fabulous guys imaged 60-something brains for us. John created a symmetric atlas for the fly brain, central brain, and the VNC. And in the meantime, Larissa in the lab developed a method to extract all synaptic clefts from the FIB dataset, the TEM dataset that I showed you much earlier, which then, if you plot this without the EM data, looks like this, which very much resembles the synapse staining that you see in light microscopy. So we can use this as a bridging channel to automatically register the EM dataset with the light microscopy dataset. And now this reference registration is being used to correlate reconstructed neurons from the EM dataset with neurons in the atlas space. The atlas is called 2018 because we did it in 2018. Then this thing has been sitting on bioRxiv for forever. And on December 31st, finally, it was published last year. So that's why this only comes up now. Okay, so making a new atlas is not always a great idea because the community likes to stick with the old atlases, and old data sets exist in different atlas spaces. And in order to be able to correlate them and work with them, John developed bridging registrations between all the popular existing atlases out there for the fly brain. So we have here the, 4 alternative atlas spaces. Here is the new 2018 atlas space, and here is the FIB dataset. So we have a registration into EM. We also have one for the hemibrain in the meantime, which is this part of the central brain, and the various existing popular atlas spaces for Drosophila. Again, code and tools are out there. In this repository, you find all of John's scripts to generate these atlases and to register between them and to use bridging registrations. And Greg Jeffries in Cambridge has developed a whole set of R packages that use these things to convert neuron reconstructions between various spaces. The templates and the transformations are stored in a specialized HDF5 format, so they're small but also accurate. And you can find them on the Open Science page at Janelia and access them through the N5 API that I'll talk about later. Okay, so a different project that we've been busy with that is also not well described because it's only in the supplementary material of the Big Hemibrain paper is how we registered and aligned together with many fabulous colleagues the Hemibrain dataset. So I showed you the video earlier in the talk that this consists of these independent 13 slabs, and their new incoming datasets with even more of 20 micrometer thickness, and each of them is imaged ideally on different FIB-SEM microscopes. And so you have a whole series of things. I'm skipping the more trivial parts here to reassemble them into a joint volume. So the first one is very similar to what you have to do for the TEM data set. You have to stitch and align the FIB-SEM stacks. So in this plot, I'm trying to show that while the FIB-SEM is meant to generate a line series, there's still a little bit of jitter going on, and you have to account for this jitter. And there are also restarting issues. So when you restart your microscope after you extract the sample, which happens occasionally, you have a completely changed orientation, and you need to align this in order to reconstruct your slab properly. So in this plot, we see that in the acquired images, the actual sample, the 20 micron slab, sits somewhere in the plane, and the rest is background and resin. I'll come to that later. But before we get to this, so after registration, you'll figure out that the milling thickness in this data set is not equidistant. And you have to account for that, so you can unstretch and unwarp the Z appearance of the stack. Then we use a very cool method by Dagmar Keinmüller to extract the surfaces of the actual samples. And once we have all that, we can register the sets of surfaces across all samples and generate a merged volume. Okay, so let's first look at the stitch and align slabs. This is very similar to old stuff that we've done for TEM data. We use the popular SIF features from David Lowe, and we extract key points across tiles in the data set and across many sections, and then we filter them by geometric consensus, so all the good features support the same transformation model and all the bad ones don't. So you can find these best models in these data sets. And then we minimize an optimization problem that minimizes credit placement between all these points. This hasn't changed much. Khaled has changed the code that generates these optimizations and made it a lot faster. And Eric Trotman has developed a framework to run this on compute clusters for very large data sets. But anyway, so the general pipeline is still this. And together with Stefan Preibisch, we've currently improved this. and we use his point descriptors to get even more control points in places where they're none, and to parallelize it better. So this pipeline is currently growing and improving. Then we come to the next step, this correct milling depth. And this is work that is based on some previous work by Stephan Saalfeld in the lab that Lou Scheffer implemented a slightly reduced version of this to apply these on these FIB data sets, but the method is still similar. So we assume we don't know what the correct milling thickness is, so we have to measure it somehow. And we assume that the sample is kind of the same all over the place because it's all neurons and they have quite similar thicknesses and stuff like that. So when we correlate sections, we should see that nearby sections correlate well, and sections that are further away from each other should correlate worse. So we can use something like normalized cross correlation for as a similarity metric, and then we get a matrix if we do this across the entire stack, and we see that the change in this similarity is not even across the stack. And we can also see that in places where the sample is compressed, like here, the correlation falls off faster. And in places where it's kind of stretched, like here or here, the correlation falls off very slowly. And what we now want to do is we want to make this matrix smooth and the same everywhere. And this is what Philip did. And by doing so, you can stretch the sample so that it's homogeneously spaced in Z. Okay. So here's another example. We can see a compression here and a stretching here, and we can see how this manifests in this matrix. And when we now optimize this away, things look more homogeneous, and we get an unstretched Z spacing. So this, of course, requires that the speed at which the signal similarity changes is kind of homogeneous across the sample. But the method, as Philip implemented it, can actually deal with this. So you can work with slow changes across your sample. It's not very reliable when you have very small data sets with very structured things that are very much unlike the neural data that we're looking at here. Okay. Next step is the surface detection. I mentioned earlier that we're using a method that was developed by Dagmar Keinmüller. She has like a 2D shortest path finder on top of a cost function that tries to estimate the likelihood that there is a surface. But what I want to show you is a little bit more recent developments that we did to deal with this. And this is where I would say, so I want to hit the drum for good software libraries at this point, where we benefit from the big data viewer framework. So we estimate these surfaces, and these surfaces have, while they're mostly good, they have some problems at strange artifacts along these slabs. So there are some places where you have dirt particles sitting on these artifacts, like this black one here. And because it sits so low in the surface and it's still very flat, the surface finder prefers to find the surface on top of the dirt particle instead of under the dirt particle. And it's very difficult to predict what kind of artifacts that you will see, because there's always something new going on. So what we need is interactive tools to be able to fix these problems, right? And what I'm showing you here is such a tool that was developed on top of Big Data Viewer. It was very simple to develop this. We're looking at a 5 terabyte data set. The slab itself is very large. We have a multi-scale representation of this thing. And we apply the surface finding and flattening deformation on the fly to this data set. And we can interactively paint into this and then save it and undo it and stuff like this, right? So the fact that we can all do this in real time on very large data sets turns out super helpful, and is the only way how to address this, because if you do this on single images and you identify regions and stuff like this, you never get the precision, right? So what I'm having here is just a simple brush where I can push up and down this deformation field and can immediately see what the outcome of this is, and then I can polish it, I can make it more smooth, and then I can pull more and less, and I can change the size of the brush and all kinds of stuff, right? Okay. So this was a little bit of a shout out for a big data viewer, and it's an awesome tool to develop these kind of things. Next step is the aligning of the slab series, and I will just show you this on an example. Here we see a bunch of these faces. So if you have n slabs, we have n-1 faces where we have to align them. So each of them consists of a bottom and a top face of the adjacent slab. What I'm showing you here is the bottom face of these transition places, and here we see the difference between the aligned or not aligned bottom face and top of face of the previous slab. And at the bottom, we will see the difference of the transformation model that we estimated compared to this already roughly aligned initial situation. So we're starting from a single affine transformation between all these tiles. That's the first step. And then we start to subdivide this. So you have to keep in mind that each of these fields of view here is 30K by 30K. So these are relatively large 2D images. These are the extractions from these slab faces at the very tip. And they're really dirty because this is the place where the knife cut through the section. And you have some ripple effects. I mean, you try to find a good surface, but sometimes there's knife chatter, so things break off. Sometimes half of mitochondria breaks out, so you have white signal where you used to have black signal on the other side and stuff like this. So it's a little bit difficult to find the correct model. And therefore, we do this stepwise. We first identify just one affine model for each of these transitions. So we zoom out very, very, very far and use, again, SIF features to find this with the consensus model. And then we subdivide this in smaller regions and do exactly the same thing again. So we subdivide this in 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5 subregions. Again, these are still large images of thousands of pixels in square, extract the SIF features, find consensus models, and then map these consensus models into an interpolated deformation field. And you see here the difference of this deformation field compared to the previous affine model, right? So you only see the non-linear part of it. Okay, and then we further subdivide this, and then we further subdivide this, and then we further subdivide this. Sorry, stopped. Yeah, okay. And we do this up to a point where, wait a second. We do this up to a point, and this would be like here, until the images are becoming, so the sub-images are becoming too small for SIF features to reliably find coordinates. And then we have to switch to a different mode. Classic optic flow estimation is basically just block matching of small windows for every pixel, and we're doing this here. So we want to estimate a flow field compared to the previous transform for every pixel. And one of the issues that you have to solve there is what a good block size is. So if you have a large block size, you can see a lot of texture and you get a very reliable estimate, but it's overly smooth because you're averaging over the deformation within this field of view. And if you have a too small block size, you may not find the correct estimates because your texture window is poor and it's ambiguous where the correct solution is, right? So there's probably ways to do this smarter, but we didn't have one because we didn't have too many samples for this, because if you have 13 slabs, you have only 12 transition phases, and each of them is weird in its own way. So we engineered it a bit. And what we're doing is we basically estimate the flow field for an entire scale space of block sizes, and we use an integral image trick to do this fast. And then each block size comes in with its own hypothesis about the flow field, and now we can compare about these scales and look where they disagree. So what their consensus set for the flow vector is, and we use that as the flow vector at this position. And this can come from block sizes of random sizes. So what you would usually get for very small block sizes, things get super noisy, and for very large, and then comes kind of a stable region. And then for large block sizes, they converge to the average affine model, so they drift off, right? And what we're interested in is this stable region. You can find this by just looking at the entire scale space. We're basically doing this for every pixel. We don't start at full resolution. So we first work with downsampled versions of the images, but eventually we do this at the full resolution of the entire data set. So that further refines these images, and well, at this resolution you can't see the difference of these flow fields. But if we zoom in and look at a few examples, you can actually appreciate how well this aligns between these data sets. So here we see the transition between the first two things. This is a zoom in, and you can also see that there are often strange differences. It's not immediately adjacent. Here's the next one. And then, yeah, again, this is the complete section. This is just a zoom in. Here's the next one. You can see that how heavily deformed these things are relative to each other, and how you have these empty areas where there's a little bit of knife chatter and distortions, but it doesn't compromise the registration, because we're approaching this from with this robust feature-based method followed up by correlation. And I think I have one more of these guys. Maybe this one. Yeah. So things are in motion. Together with Stephan and Scientific Computing, we are currently improving this alignment workflow to make it even more robust, and to add manual correction tools to work on to improve these data sets, to improve the registrations where they fail, because that still sometimes happens if you have completely garbled data. Then it's often difficult. Then it's sometimes difficult to find these places. For the hemibrain, I have to admit there were no manual corrections done anywhere, and we have only very few places where things weren't aligned properly. So they haven't compromised the connectome reconstruction so far. All right. Now, hopefully the last piece, I want to talk a little bit about data backends. So for these, for both data handling of these large registered data sets, as well as the deformation fields that we're extracting from them, we needed a data format that allows us to store things in parallel and access it in small chunks, so we can interactively modify it and visualize it. And so we looked at various formats for this. And just to give you a brief overview, it's just what can you do with the standard image formats? So when you store 2D images, there are billions of image formats out there. So every microscope vendor has probably their in-house format. Standards are TIFF or HDF5, and you should not use anything else but TIFF or HDF5 for 2D images. Right? Because TIFF supports compression, HDF5 supports compression, so why use anything else? Fine for the web, or things PNG and JPEG are probably appropriate. If you want to load a small region from one of these standard formats, if it doesn't support any chunking, you unfortunately have to load the whole thing, particularly when it's compressed. So if it's not compressed, you can play tricks, and you can seek on the file system, and then make a stride jump, and then seek again, and so on. So that works. But if your data set is compressed, you have to uncompress the byte stream, and you have to crop it out. This is a lot of I/O. This can be reduced by using a tiled format, and there are a bunch for 2D images. HDF5 is again in the game. TIFF supports this, and then there are various web formats that support this, like Zoomify, Google Maps, or CatMate. And that helps you insofar as that you have to load only the chunks for a small region that are covered by the region of your interest. So what to do when you have 3D or 4D data, and you use a 2D image format like TIFF, for example, you just add slices. Again, there are a bunch of formats. HDF5 supports this natively, which is great. And again, when you want to load a small region, of course, you can save to load the rest of the slices, but you still have to load the slices that are covering that region of interest. So we can again benefit from data sets, from data formats that tile things, which are the same as you've seen before, where we load only the tiles that are relevant for this data set. So here is a little bit of an issue. You would like to have these tiles to be very small, so you have to load less data. But as you make them smaller, the hairier it gets for the file system. So if your 2D tiles are like 5 by 5 pixels, that would be ideal to not load too much data. But to create a file on the file system of 5 by 5 pixels wastes usually a lot of space because there are blocks in the file system, and you don't want to waste this. So this is discouraged. Or if you have this in the web, you make a query request for each of these files, and then you die in latency, and that's not great. Okay, so you want a native format that supports these kind of things. Again, HDF5 shines here because it supports this as an n-dimensional data format for data. You can also associate metadata with this. There are also some other things like Divid, BOSS, or Cloud Volume that focus mostly on 3D data. That becomes difficult when you have to deal with 4D data. Because now we can load individual blocks instead of 3D blocks that are reasonable in size, or 4D blocks that are reasonable in size for each query. And that's great. Unfortunately, HDF5 parallel writing on a cloud platform, for example. And that's why we came up.
Yeah. Could you repeat what after unfortunately? I think your video was shortly not working.
Oh, it doesn't. It unfortunately doesn't support parallel writing. So you can parallelly you can compress in parallel with a library that was published by BitPlane recently on a single platform, but you cannot write in parallel when you work on a compute cluster into the same data set. So the chunks in a data set depend on each other. The arrangement of the chunks in a data set depends on each other. And so you have to write things sequentially, which can be very slow when you work with very large data sets. Okay, so that's why we took all the good stuff that is in HDF5 that we like and developed the simple N5 API. First, we started with a file system backend that stores the chunks as independent files. But we discovered that you can express the more fundamental concepts of this, like creating and deleting groups, data sets, metadata, and blocks as a general API. And you can now implement various backends on top of this API that support file system-based backends, ZAR, which is very similar to this one, cloud-based backends, and others if you wish so. But these are the ones that we have. And then we developed bindings that build on top of this API and use ImageLib2 cache to immediately make these things available in ImageLib2. We developed the method so you can extend compression schemes. And the most recent thing that I tried is actually a JPEG compression scheme to have stuff that is more rapidly available for web display. But you can do whatever you please, right? So support exists now for a bunch of backends. It's AWS, Google Cloud, HDF5, ZAR. Then this is a compressor for the ZAR support for JPEG. And in the meantime, there's quite an interesting community working on these things. I'm actually pretty excited about this. Okay, we have a bunch of utilities for this. These are command line utilities. These are utilities to make multi-scale data sets and some other conversions for tera that are N5 Spark. And we also distribute this thing with Fiji. Currently, it's in the main distribution. So when you download a fresh Fiji, you get N5 and the N5 plugins for free. So you don't have to add a new update site or anything. And yeah, there are Maven artifacts. The N5 stuff is inside Java, and the utilities that I mentioned are not so stable. Sit on our own Maven repository. Right, and this is, I guess, the end of it. So I will close with a screencast that I recently made for how you can use these things in Fiji. What I'm showing you here is a plugin to open things. So you just search for N5, import. And you can import things through a big data viewer plugin or as a small crop data set in Fiji. You have to keep in mind that ImageJ isn't made to deal with large data sets, so you have to crop a region from a data set. And what we're watching me doing here is to open a data set from these recent organelle reconstructions in FIB-SEM of whole cell images that sit on AWS. So we distribute the data publicly on AWS. I'm showing here the web interface that looks into the AWS storage, and then we can see exactly the same thing in the browser in Fiji. And
Stephan, I have a really quick question about this.
For it.
I was trying to use this yesterday, and this S0, S1, S2 naming system, that has something to do with it being a scale pyramid, right? Can you just explain a little more about that, and if you could name it other things and it would still recognize this?
Yeah, so that's just a naming scheme, because the scale pyramid is not a native part of the N5 API. We have metadata on top of this and in the attributes that specify what the resolution of the scales are. And the scale pyramid is basically just a pyramid downsampled by arbitrary scale factors. And the scale factors are defined in the metadata. Yeah.
I was just trying to open a data set that I had written, and I didn't create a scale pyramid. Do you need to do that before you can open it?
No. You can. So I'm open. So what I'm opening here is basically just one data set of the scale pyramid. So each of these S data sets is just a data set. Okay. And the scale pyramid consists of several data sets. So if you just want to open one data set, you just do it.
Good.
If you, with the Big Data Viewer backend, with the Big Data Viewer plugin, you can also open the entire scale pyramid, and then it will use the entire scale pyramid to render things quicker in Big Data Viewer. So when you zoom out, it uses lower scales than when you're zoomed in. But if you want to open exactly one data set, you just do it. That's OK. And if you want to create a scale pyramid from a data set, then the N5 Spark repository contains the code to do that. And you can run this on a Spark cluster, but you can also run it locally. And there's instructions how to run them locally.
OK, good.
But it only makes sense if your data set is large enough so that it matters, right? So if you're at a few 10,000s of pixels in a dimension, then I would start making scale pyramids.
Yeah, I think that I opened a ZAR and then somehow in Fiji tried to convert it to an N5, so I could open it in Big Data Viewer, which is what I wanted because it was a big data set. And it did that automatically. It took a while, and then with an even bigger data set, I ran out of memory. So.
So you can now. So it depends a little bit. There's a historically grown set of things. That's maybe a bit unfortunate. You can now open ZAR directly with these plugins and look at them in Big Data Viewer.
Okay.
So there is
look into that.
So if you control L N5, there is this N5 viewer plugin now, and we updated this so it has the same dialog, and you can browse into a ZAR container and open these data sets directly. So you don't need a conversion.
Yeah, I may need to crop it though, so it won't.
I don't know. If you look at it in Data Viewer, you don't need to crop it, right?
Okay, so that's good.
If it's just for visualization, then you don't need. If you want to open it in Fiji to do some stuff and to I don't know, do some ImageJ stuff, then you need to crop a small region. So this here, for example, so now I'm opening things with the Big Data Viewer plugin, and I don't know if I move the movie forward a bit, so you can open several channels at the same time, and then you see the organelle predictions and stuff like this, right? You can adjust colors and whatever. And that's all multi-scale data sets, so they load quickly when I'm zooming in and out and stuff like this. Yeah.
Okay.
I can do the same stuff as R. Okay.
If I run into problems, I may shoot you an email.
Yeah. Perfect. Okay.
Thanks.
So with this, I have to finish, and I want to thank everybody who helped us with this, the lab, great colleagues, and the people who generated the team data, the FIB-SEM data, the light microscopy data, and the wonderful open source community that helps us with everything. And with that, I will stop this sharing. Thank you.
Thank you very much, Stephan, for this great presentation. So are there questions? As I said, please feel free to use the raise hands feature at the bottom. Okay, Christian?
Yeah, hi, Stephan. I just had also chat with Boas. We thought with this lens correction thing, yeah?
Yeah.
I mean, it's a confocal, right?
Yeah.
So it has a scanner, so it's doing this the whole time.
Yeah.
So I think maybe it's doing it. It could be right that the scanner is maybe just accelerating a little bit and slowing down along the x-axis. Maybe that's
possible. Yeah.
And then I think the idea of Boas was to, if you want to check that in these confocals, I think you can take the same image, but you can rotate the scanner.
Mm.
You could try if then this pattern rotates.
Absolutely, absolutely. So I think if the aim is to find out what the cause of these deformations is, then we should do all this. What we were a little bit opportunistic when we did this. We just wanted to get rid of them, and getting rid of them worked without understanding much what it really is. So we just calibrate every microscope after the technician was in the house, and that seems to work very well and gets us into subpixel stitching errors, which is exactly what we wanted. Right.
Fair enough. I just had it.
But that's very opportunistic. I agree. So it would be interesting to know what the reason for this is.
Or not. I don't know. I mean, this would be a natural thing why it's a bit asymmetric in X and Y.
I agree. It's a good point.
Are there more questions? Yeah, Martin? Please, you have to unmute yourself.
Yes. Yeah, thanks for the talk. I have a question for the alignment of the slabs in the big FIB-SEM volumes. So there's quite some dramatic changes in these volumes. So that might all make sense from a data perspective, but the question is, do you have a readout for how well this matches the actual physiology that you want to find out? Or would you still require some kind of orthogonal modalities, like something like light microscopy or X-ray tomography that could give you, when you register it, an idea of whether what you correct is actually physiological?
So I would say the major influencing factor on local morphology is your EM preparation protocol and not this alignment stuff. The alignment has so there's some warp going on, but it doesn't change sizes of objects by more than a factor of 2 or something like this, right? So you're within a reasonable range compared to what you do to your sample during osmification and water substitution and stuff like this. So we also have the registration to the atlas, but that doesn't capture anything local, right? Because the light microscopy resolution is so vastly lower than the EM data resolution that this shouldn't have much impact. The other point is in this particular data set, the emphasis is not so much on preserving local morphological features, but just trace neurons. And for that purpose, it seems good enough. For the cell biology data sets, like in this COSEM data set that I showed last, it is more relevant, but these are also high pressure frozen samples. And what I've seen so far is that the alignment and the axis thickness correction makes things better rather than worse. I don't know how satisfying this is.
Yeah, I think a gold standard would still be having an orthogonal modality to check somehow that you can do some
so what they
imaging.
do is they create X-ray images of the slabs, but they're also like close to light microscopy resolution. I mean, that not super high resolution. So you don't see the small morphology changes. But that's
at least you can be sure that you don't accumulate some artifacts and then it runs off at some point.
Yeah, so we don't accumulate artifacts because what we always do is we average the transformations from all sides. So we always try to stay as close as possible to rigid transformations, which prevents accumulation.
Okay, thanks.
So in the slab alignment, for example, so in the stack alignment, this is actually what's happening. So every tile tries to stay rigid. And then you get an average deformation for each, the minimal deformation for each compared to a rigid. And then for the slab alignment, because so every block can just has 2 transformations on each side. We take both sides and we warp both sides to the midpoint of the 2 transformation models. So there's a forward and inverse transformation. We just go to the middle. And then you interpolate across the stack. So there's no accumulation.
So are there more questions? Otherwise, I have a few comments. Like first, like you said, you call this lens distortion, but I actually agree with the comment you made earlier that I would actually call this kind of system distortion, because I think in an electron microscope, I think you can grasp quite quickly which elements are relevant. So an electron microscope is, I wouldn't call it primitive, but it's, I guess, more straightforward when you you know what I mean? Like if you, for example, compare this with a normal light microscope, you can have multiple lenses, you can have multiple optical elements in there, and I think it's a little bit. So you have to take multiple elements into account when you come up with a model, which might not necessarily be or can be modeled like a normal lens. Like as I said, different kind of optical elements. For which
So you're right. I think I would call this system distortion. That's absolutely correct, because it compensates for everything in the system, and it's an end-to-end thing, right? But also an electron microscope is not that simple. Because it also contains several electromagnetic lenses along the path, right? And in the end, you still have a camera that images this scintillator with the lens, and so you're basically compensating for the EM lens distortion along the entire path, plus the lens distortion that comes in from the imaging camera. And that was particularly important for Davi's data set. Because he had this camera array of 4 cameras that were mounted somehow to look at the exterior areas of the scintillator, so where the data was most distorted, and the mounting of the camera was just manually calibrated. So some of them had a tilt and a little homography because they looked at an angle at this scintillator. So yeah, but you're right. It's a system distortion. Yeah.
And then also to the 6 camera where you said that it was not that easy to grasp. I would say like this sounds like as if the light microscope might be a little bit unstable because like depending on when you take the measurement, maybe there's some kind of an element in there which kind of is not consistent in its performance. That's why it kind of the variance of the performance in your graph was so high, but I don't know, just a random guess. And then I only have one last thing. So you have as an explanation or as a nice example for how you do the transformation, the brain. But I think you use the brain because that's the underlying project you're working on. But the unfortunate thing with the brain is that it's highly heterogeneous. So it would be great as an example for a testing tool to maybe have a sample which is a little bit more in itself symmetric, such that you can actually like some kind of a real life ground truth thing or so. That sounds maybe a little bit odd, but just as a, I don't know, some kind of imaging a muscle fiber or something like that. So where you actually have a little bit more reproducibility to actually check the performance on a real life thing as well. But just as a, but we can talk about this also.
So you think the brain is not real life?
No, it's just like it's just for a new software tool already kind of it's the most complex thing ever. So but just as a
so for this actual distortion correction, for example, I said we benefit from the fact that inside the neural pills in the brain the structures are relatively homogeneous, so we can rely on this similarity function to behave reasonably. Okay. We have tried to do exactly the same thing at super high resolution on cell samples. And we can see some places where it fails because, for example, when you transition rapidly from intracellular space into the nucleus, that looks different. And you can see this. And then if you overcompensate this, you start stretching out the nucleus and compressing the cytoplasm. And that's not good, obviously. Right?
Yeah, no, but thanks for commenting on this. Are there more questions? If not, then I would say let's thank the speaker again. So thank you, Stephan. Thank you very much for our first talk actually in the seminar series. And please stay tuned. So we have on February 2nd, we have our second talk within this year given by Nina Streich from the EMBL. So yeah, and again, thank you very much, Stephan.
Thank you so much.
Bye.
Bye. Thanks.